So I'm going to talk about a couple things today, and then I do want you to watch some videos before Monday, so do that in your 6th or 7th period class, if your teacher lets you. Some of it I've already covered, but it'll be a little more detailed, and I just want to kind of keep the ball rolling here pretty quickly, so I want to spend more time in class solving problems and watching demos, and then less time in class me talking, because I feel like I can ramble on and on about electromagnetism forever. So all that being said, let's talk about some stuff. First of all, something I haven't talked about, magnetic field. Well, I have talked about that. The magnetic field, the symbol, capital B, obviously because magnetic starts with the letter B. The units, we can use our equation for magnetic force on a charge. Magnetic force is Q times, and a lot of times you'll see it written like this. But once you learn vector calculus, you learn that Q times V cross B is equal to QV cross B, which is equal to V cross QB. And so we just write it like QV cross B. That's fine. Those are just properties, kind of like those are vector calculus vector operator properties that you learn, the distributive property and the commutative property and all that. Well, there's more properties like that you need to learn whenever you get to vector calculus. Just understand that this is just Q, charge Q, times the velocity crossed with B, which the magnitude of which is QVB, sine of the angle between them. Then use the right-hand rule to determine the direction of the resultant vector. Pointer finger in the direction of V, middle finger in the direction of B, and your thumb. Even if it's not a 90-degree angle, it's still going to be the same thing. And then your thumb points in the direction of the force. So if it's moving this way, magnetic field points down, it feels a force into the board. Okay? So if they are perpendicular, the velocity and the magnetic field direction, the sine of the angle is 1, and so the magnetic force, magnitude, will be QVB. So I can get the units for B using this equation. The units are just the units of force divided by the units of charge times velocity. And so that's obviously newtons per coulomb, but then the inverse of meters per second, so seconds times meters. So it's Newton seconds divided by Coulomb meters, which gets the name what? Does anyone know what the unit of magnetic field is? The derived unit? It's named after a car. Tesla. Capital T.
Wasn't it named after like driving Tesla?
Yes.
No, it was named after Edison.
And it is, 1 Tesla is a huge magnetic field. So very often we use the magnetic field, the Gauss. It's named after a car also. No, it's named after a guy named Gauss. Capital G. And 1 Gauss is equal to 10 to the negative 4th Tesla. Gauss is still kind of an SI unit, but it's in the CGS system instead of the MKS system. Centimeters, grams, seconds. So
is that just because the cross product is like QV cross B is the same as V cross QV? It's not. It doesn't like distribute or anything?
no, it doesn't distribute. No. It's different.
Okay.
It's still a vector multiplication, right? It's vector multiplication, and so it's not. Yeah, it's more like A times B times C is the same as B times A times C. It's more like that. It's more complex than that, but that's vector calculus. That's college calculus. Okay, so that's the unit. Again, 1 Tesla is a very large magnetic field. 1 Gauss is 10 to the negative 4th Tesla. The magnetic field of the Earth is typically about half a Gauss. Okay, so it's pretty small. Pretty small. All right. Let's talk about something very interesting that led to one of the greatest discoveries.
How many gauss is like a typical neodymium magnet in a hard drive, for instance?
1 Gauss, like a single Gauss
Like how
on the
strong-
order.
How strong is it?
I don't really know.
Okay.
Okay.
I don't know how much you
That's way beyond the scope of this class. So something that's interesting that led to a very important discovery. Let's say I have a magnetic field pointing out of the page, out of the board, and it's a uniform field that fills a large
High school.
region of
It's now
space.
time for juniors to be released to the,
Oh, that's you guys, right?
if the G Hall only, has completed their attendance, just the G Hall juniors may be released to the auditorium. G Hall only after your completed attendance. Thank you.
Let's say we have a positive charge that's moving within this uniform magnetic field that has a speed v. Magnetic field is pointing out towards you guys. And I want to determine the direction of the magnetic force. What direction does the magnetic force on this charge point? Did you bring tardy passer?
Yeah. April Fools. It was congregating.
You gotta love it whenever there's 10 people in the bathroom and then 4 of them just take turns in the stall hitting their dab heads.
What direction, Logan, does the magnetic force point?
It would be perpendicular to the velocity. No, it'd be this way. Right? No? I don't know.
Trent and Alex are correct. It's down. V cross B force.
Oh.
Magnetic field's coming out towards
Oh,
Wait,
yeah,
hold
yeah.
Say that again? Oh, like
you.
the
V
V.
cross B.
Oh, it's going into.
Wait.
No, it's going out.
Oh, what?
My middle finger's pointing at you guys. So it points down.
Oh, I could have guessed that.
No, that's your left hand.
Yeah, but
It's gotta be right hand?
it's a right hand rule, not a left.
It's the right hand rule. No, you got it like this. Palm towards the back. V cross B, direction of your thumb.
You're making this more complicated than it has.
Yeah.
I did it.
Okay, good.
I know.
So it's going to point down. So that is the magnetic force on this charge.
At this time, ST Hall teachers, if you have completed your attendance, ST
I'm a
Get
teacher
it.
for the day.
juniors, please report to the auditorium. FT juniors, if your class is all juniors, teachers come on down with them.
And so it's going to still be moving to the right, but it's going to start curving down. Okay. So when it's here, remember this is charge Q. And remember what we're doing here is calculating the magnetic force direction using the cross product given by the equation this.
The equation.
The equation this. And so now it's going to be moving down and to the right. What direction is the force going to be pointing there?
It's gonna be like that.
It's gonna be like still down.
Gianni's right. He's saying it's
like
not straight down.
perpendicular to.
It's still perpendicular,
Yeah, that's what I said.
but now it's pointing down the velocity this way, magnetic field that way, thumb. Now it's down at an angle.
It starts spinning. And it's like sine of theta, because cross product.
Yeah, but the angle is 90 degrees, so the sine theta is going to be 1.
Yeah.
So what kind of motion do you think this positive charge is going to be moving in?
It's gonna start spinning in a circle.
It's going to be moving in a circle.
Wait, really? I mean, why won't it,
At this time, lower H100 Hall, to the auditorium. Teachers, make sure that you have completed your attendance. Thank you.
so why doesn't it lose the force once it like gets where
Why doesn't it? Wait, say again.
So the sine of some angles are going to end up being 0 and it'll have no force, right?
Yeah, but the angle between V and B is always going to be 90 degrees. In this case, it's always going to be 90 degrees,
Why?
even after it starts moving, because it's moving in this plane,
Because
and the magnetic field is perpendicular to that plane.
magnetic field is staying constant this way, but velocity is still changing, but that doesn't change the fact that there's a 90-degree angle here or here.
So when does it end up canceling?
Whenever it's going the exact same direction as the magnetic.
Yeah, if it's not moving perpendicular to the direction of the magnetic field.
That's it. This
So
is
you're
just
saying the magnetic field is into the board, right?
No, it's out.
Coming out.
Out.
It's coming at us into the board.
The arrows. You see the arrowhead coming at you.
Oh, okay.
The X is going into the board.
At this time, H.
Oh my gosh,
200,
Mr. McCandless.
H200.
We got
and
stuff to
the
do.
F hall. To the auditorium, juniors only.
So
And
if you-
teachers, if you have all juniors, come on down with them. It'll be a cool experience. Thank you.
Now, if you were to solve that equation for V, and then you were to integrate both.
Don't get too far yet.
Okay.
You don't need to integrate here because
Well, I was gonna say, if you were to integrate both sides, you end up with the equation for a circle. That's it. If you solved it for V and then integrate both sides.
no, we just want to recognize. Check it out. We know that the object is going to be curving continuously, right? We also know that the force is always perpendicular to the direction of motion.
Uh-huh.
How much work is that force doing on the charge?
Oh,
None. Zero. Remember, work is the dot product of force and displacement. Delta X, delta S, delta D, whatever. And so the angle there is always 90 degrees between those two. And so there's zero work being done. That force is pointing perpendicularly, so it's pointing towards the center of a circle in which that object is going to be curving it. Okay. It can be. So maybe the magnetic field isn't strong enough to get it to go into a complete circle, but let me show you a quick video.
So there's no work being done though.
No work's being done.
Well, what does the work do?
There is no work being done. The charge is not changing its energy in any way. It's got the same. Remember, if net work is being done on an object, its energy will change. That's why the Earth can go around the sun for billions of years without its energy changing, because no work is actually being done on the Earth. No network.
Okay.
Yeah, it's weird. It's weird to think about. It's weird. Kind of doesn't make sense, it seems like.
Because you said like if something's going in a circle, it's got to be constantly accelerating. So to me, if it's constantly accelerating, there's got to be some sort of force.
But that doesn't mean that that force is doing work on the object.
Okay.
What?
Wait, so I can't, so we can't work.
Did Trent say something important?
Yeah.
What?
For once.
Magnetism is a conservative force.
Yes, magnetism is a conservative force.
Oh.
Yeah.
Yeah, that makes sense.
Okay, so here is this isn't a proton beam. This is an electron beam. Like I showed you yesterday, this is a much more sophisticated electron emitter. It can actually emit them in a single stream. And there's no magnetic field now. We know that because they're all moving in straight lines. But then you start applying a magnetic field, and you get the beam to deflect. I think it starts, yeah. And you increase the magnetic field.
I think the cameraman has Tourette's.
Yeah. And once the magnetic field gets strong enough, the charges then can move in a complete circle within the enclosure.
And then they can collide into each other.
Yeah.
And then make a boom.
And so there, that you got a perfect circle there.
So
And one of the labs you're most likely going to do, and when you go to college, I did it at my community college. You'll actually do the lab where you do that. You have control over the magnetic field that gets generated by the Helmholtz coils, and you measure the radius of that circular arc, and you can actually determine the charge to mass ratio of the electron doing that.
I'm not going to college.
For those of you that go to college, obviously Mr. Henderson's not going to
I'm going
college.
to be the first engineer who didn't go to college.
Okay, so does this make sense? So a lot of times you hear magnetic forces do no work. Magnetic forces do no work on moving charges that are free, that are moving through free space. Yes, magnetic forces can do work.
As long as they're paying rent.
As long as they're. Oh my gosh. Okay. So it turns out, a guy named J.J. Thompson, does that ring a bell for anyone?
Some chemists.
Maybe.
Physicist, chemist. He discovered a particle, early 1900s.
Or an electron.
He discovered the electron, right? And by discover the electron, he proved the existence of the electron. And he used something just like what we saw. Now his setup was a cathode ray tube we talked about yesterday. They didn't have the technology to have that nice beam of electrons that went in a complete circle. So his experiment was actually a lot more difficult to perform. The math was a lot more complicated, but essentially it boiled down to you have these charges moving in a magnetic field that you have control over, and they curve. Okay, and by measuring the curving of those charges, you can actually work out. I don't know why you erased all that. I probably shouldn't have. You can actually work out. Well, let me just show you. So pretend that the picture that I had up here is still there. Okay, we know that the magnetic force it simplified the magnitude of the magnetic force is just QVB, because the angle between the magnetic field and the velocity was always 90 degrees. But we also know it's a centrifugal force. So it's mv squared over r. Those cancel. And then so we can essentially say, I can solve for the charge to mass ratio. Both of these were unknown when J.J. Thompson was doing his work. And we could say that is equal to the speed divided by the magnetic field times the radius of the circle, right? You got me? You following? So magnetic field, they could measure. They had devices that they could determine what the magnetic field was and set their dials and be like, okay, the magnetic field strength is this. The radius of the circle, again, it was more complicated with what J.J. Thompson did. But in today's world, we can get those beams to go in a perfect circle, and we can measure that radius relatively easily. But we got to know the speed that the electrons are moving. If I knew the speed, then this simple equation tells me what the charge to mass ratio of the electron is. We couldn't know the charge or the mass. We couldn't know those numbers per se, but we could know the charge to mass ratio. And once that was figured out, just a couple of years later, maybe even a year later, a guy named Millikan came along and did a called the oil drop experiment. It's a very ingenious setup where you had charged oil droplets that you'd vary magnetic and electric fields and watch until they fell with constant speed, and then he was able to figure out the individual ones. But this was the starting point here. The thing is, how do you look at a beam of electrons and know how fast they're moving, right? Especially in the early 1900s. How do you do that?
You squint really hard.
You squint really hard.
One Mississippi,
Yes.
two Mississippi.
So the way that you do that is with a velocity selector, a charge velocity selector. And so on the next quest assignment, there's going to be a few problems like this. There are a few problems like this. So what you do is you take a charge, you take an electron emitter, like what I have that I showed you yesterday, and you just fire it at an opening, okay? But when it goes into the opening, you have, you put essentially a capacitor, right? Capacitor plates or charged plates. One is grounded, so it's at 0 volts. And you have the voltage that you dial in for the top plate, so that creates an electric field that points down, right? So the electric field points that way. And I only have the electric field here. It's not here. It's just here, okay? But then I also generate a magnetic field within this entire space that either points in or out. You want the electric field and the magnetic field to be crossed, okay? And then we're going to use positive charges. Remember, if it's a negative charge, you just flip everything. But we're going to fire a bunch of charges through, and the ones that make it out are the ones that weren't deflected at all. The ones that went through with no net force because they end up leaving, right? If they end up leaving, they're leaving with the same speed they came in with. Otherwise, the electric field or the magnetic field would have deflected them, It made them hit the walls here, and they would never have gotten out in this region here. That makes sense? So let's say that this particular charge is going to make it through. Right? First of all, if this guy is positive, what direction? I'll put it in green. No, I'll put it in red. I'll put it in purple. I got a purple in here. What direction does the magnetic field need to point in order to counter the electric force, right? We want the electric force and the magnetic force to cancel each other out. Obviously, we know the electric force is going to point down, so we want the magnetic force to point up, and we want it to be at the same magnitude. If they are at the same magnitude, then the charge makes it all the way through and doesn't get deflected.
So point out.
Point out.
Yeah.
Yeah, towards us.
No, it would be the in because you want it up, right?
You want it up,
Yeah, so it'd be in the board.
so it'd be into the board.
Because my middle finger's pointed at you, Mr. Green.
Whoa.
I'm writing you up. Yeah, the electric force, when the charge is in here, the electric force is going to push it down. So we need the magnetic force to point up. So we need the cross product of the velocity and the magnetic field to point upwards. And so it's into the board, right? So the magnetic field,
Oh, okay. I see.
and it's in the entire space here, even over here, especially over here, where it's more important.
So I guess region, oh, that's right.
So these are our B field directions, okay? And so that means as the electron goes, as the proton, or the positive charge, it's not a proton because it has a charge, as it moves through here, it feels no net force. Now, you shoot a beam of them in there, all at different velocities, but the only ones that make it through are the ones that felt no net force as they were traveling through that region of space. Because any other ones would either be deflected down, up, left, or right, and so they wouldn't make it out. So if they came out here, you would know, or could calculate exactly how fast they're moving. Excuse me. And then once they're here, they are now going to move in a circle because now there's no more electric field. Or at least you dial in the magnetic field so it doesn't end up hidden over here. You want to get a nice circular path whose radius you can then measure, right? Again, when J.J. Thomson did this, it was a lot more complicated because he didn't have the technology, a big enough chamber that you could actually get a circular path for the electrons to go. It's just a curved path, and so the math was a lot more tricky. But we can do this today. And so let's say we have this setup, and let's say that, so this is how the electron was confirmed to exist, right? They knew, this is how J.J. Thomson said, okay, we got a particle that has charge and mass that we've never detected before. We know it's the negative charge carrier because of the way it interacted with the electric and magnetic fields. And so that's essentially cathode ray tubes, and J.J. Thomson ended up leading to the confirmation of the existence of the electron. So this setup, though, is a very common physics problem when you learn about crossed electric and magnetic fields and what they're used for. And so say that this problem, let's say this is a problem. Let's say this is a very similar problem to number 19 on your quest assignment. Hint, hint. So I have a magnetic field that is directed as we discovered, as we pointed out. I can't talk anymore. Today's Friday. Good. Today's Friday. So we know the magnetic field points in to the board. Let me draw it here too. It's 0.3 Tesla. The voltage, 2600 volts. The spacing here between these two capacitor plates is very small, 0.8 centimeters, so less than a centimeter. The radius of the arc that the charges actually take as they go through region 2 here, 0.26 meters. And the charge itself, let's say, is 7.9 times 10 to the negative 18th meters. And our unknown in this problem might be the mass of the charges. You know, a problem like maybe number 19 on your quest assignment might give you a setup like this and might ask you for the mass of that charge. Okay. All right. Notice that the magnetic force equation, the electric force equation, don't involve mass, right? They involve charge, they involve voltage, they involve distance between the voltages, the charged plates that cause the voltage. They involve the speed. They involve the magnetic field, the electric field. They don't involve the mass. But we just showed that we can get an equation for the mass from region 2, or an equation that has mass in it by looking at region 2. Because in region 2 there's no electric field, and so in region 2 the only force acting is the magnetic force. And let's just talk about the magnitudes. We know the direction, so let's just focus on the magnitudes. The magnitude of that force, Q V cross B. Actually, let's write it like this because cross products are vector products. But the magnitude of the magnetic force is just going to be QVB. Again, because the velocity vector at any point here is always going to be perpendicular to the magnetic field, so the sine of the angle is always going to be 1. And we also know that that is a centripetal force. So that's where we get the mass into the equation. Okay. Bet. All right. So here's an equation that involves mass. I can actually simplify. So one of the velocities cancels from the left side. So I get QB equals mv over r. What's my problem though? To solve this for mass, I need to know the charge, I need to know the magnetic field, I need to know the radius of curvature there, and I need to know the velocity. Not the voltage, the different V's. So when you're dealing with voltages and velocities, I like putting a little tail on my V, on my velocity, right? Yes, velocity is typically lowercase, voltage is typically uppercase, but I can't tell when I draw them, when I write them.
That's square root.
What's that?
Square root.
Stop it, Timothy.
That looks like a swan.
All right, so that's the problem though, right? If I wanted to use this equation to calculate mass, I need to know the speed, right? And I don't know the speed. So this is where the velocity selector comes into play. I can use this. I can use this right here to determine that speed. Okay.
Yes.
How do I do that? Because I know that there is a magnetic force here in region 1 that involves the speed of the charge. And I also know that the electric force and the magnetic force are canceling each other out there. So I can say that in region 1, I can say that the electric force has to equal, the magnitude of the electric force has to equal the magnitude of the magnetic force, right? What am I doing on time?
2 minutes.
Are you serious?
April Fools. April Fools, but I'm serious.
Oh crap, okay. The electric force, Q times the electric field, right? Magnetic force, QVB, right? Where this V is our velocity. Electric field, I don't know if you remember, it's been a while. Voltage difference, which in this case is just the voltage, because the other side is at 0, is electric field times distance. Therefore, the electric field is voltage divided by distance. That's voltage, capital D. So here I have Q, and actually I can cancel the Q's. So I have voltage divided by the spacing between the plates. Remember, you do the integral of E dot dr, right? That's where that comes from. And that's going to equal the electric field. No, I'm sorry. That's going to equal velocity times d. So I can determine the velocity here. The velocity here is going to be v over, I'm not going to write dv because that's going to look like the differential of magnetic field. So I'm going to write b times d. Okay. And then, since we're about out of time, I'm just going to tell you. Next, I would plug this in for the speed there. And this is, see with the velocity selector, this is what we're selecting for a velocity, and we can determine what that velocity is. And then we plug it in there, and at that point, our mass is the only unknown.
Exactly.
Again, might be similar to problem number 19 on your quest assignment. Maybe. Have a good 3-day weekend.